Oh. So people have probably seen this picture before, which I think tries to summarise what's going on here. There's an occultation, if you like, of how visible geometry works, right? And they're replacing it with this idea that we're living on a space ball. Yeah, total nonsense. Yeah. So I'll just set a bit of context there. This might be a bit of repetition, but I think it just makes sense to go for a few slides that.
Sorry, Gav, see, just before we go into this, because I'm forgetting, in case there is anybody new here, what's established so far is that, there's two different geometries at play. There's the geometry of the space that we move around in, and then it's how that appears to us through our vision. And that vision has a separate geometry to what the actual space is. Right? So this is where we're talking here about the geometry of vision and how things appear to us in the visible field. And that's it. It's just a quick one for anybody that may be wondering what the fuck we're talking about, or the relevance of this.
Yeah. So the picture I've got up on the screen shows on the left-hand side our tangible world, the world we move in about in. There's a little figure there, and we've got all kinds of objects in our daily life, right? Cylinders, cubes, pyramids, balls, blocks, you name it, right? And that's the world we live in, the physical substances, objects, stuff, right? And that 3D world is where we move in. And as you quite rightly said there, there's another visual world, which is different from the tangible world. And that differentiation, or the ability to attend to that difference, to discern it properly, is something that's not easy to do, because we all have eyes and we use them every day. So it's not always obvious to us that there's something different at play.
Yeah.
We just tend to think about the physical objects all the time.
Yeah.
But anybody can see for themselves that objects change shape, depending on your position, the angle at which you're looking at it. So a table doesn't look like a square table from a side view, or from an oblique view. It looks like a trapeze or something completely different, right? So, and the ability to differentiate these two things is really important in understanding how the lie is working. Yeah. So your visual space or your visual perception has everything to do with spherical geometry, which is what we're talking about here. I'm not going to go into detail on the other things on this picture, but so if you like, there's two different geometries at play here. There's the geometry of the physical space down at the bottom, which is everything to do with substance, construction, storage, manufacturing, transport, engineering, mechanics, all the things that we do in our daily life and people build and construct with, right? Parallels, levels, plumbs, it's all Euclidean geometry. And it's all part, if you like, of natural science, right? And part of our human nature, our lived life, right? Our physical reality. And these things, as far as I'm concerned, are all objective truths, yeah? I mean, anybody can pick up a brick, anybody can play with water. So all these things is something that, they just are there, right? Yeah. And we can all experience them. We don't need to reason about why they're there. We can speculate why they're there and who built them and who made them and all that kind of stuff. But at the end of the day, human life and the world in which we live in, and we can observe it. We can, discover how the laws are, how they operate, but we don't really have a clue who made them and what's behind it all, right? So, and the top half of this is the geometry of visible space, which, as far as I'm concerned, has been used in things like astronomy, the celestial sphere. It's used in navigation, it's used in dialing, which is like sundials and telling the time and clocks. It's used in surveying, geodesy. So everywhere vision is used to calculate something, or calculate often based on assumptions, then it's the geometry of vision that plays the role. Yeah. And there's different kinds of visual spaces. Spherical is something that people don't realize that that's how their vision works, and a lot of that is then changed using language, and mathematics is a language, to give us all kinds of stories about space balls and globes and, beliefs and cosmologies. And as far as I'm concerned, all these things are subjective, Dale, right? There's certain truth to certain mathematics. I'm not denying that, right? Like Euclidean geometry, the very fact that it's used so successfully tells us that.
Yeah.
But at the same time, all these cosmologies and space balls and infinite universes, these are all things just based on mathematical physics, yeah? And there's absolutely no proof for any of the stories they're telling us, yeah? So, again, this is the example of a daily life. There's a picture out of my, general world here at the top. I know that fence is really, the square sections, so to speak, yeah, or oblong rectangular sections, sorry, and that the slats of wood, they're all the same, and that the barn here on the left-hand side is also, rectangular. But the way the whole stuff looks to the eye down at the bottom, that's what it really looks like. Well, that's what we're seeing, right? We just don't necessarily, we're not aware of it, Dale, because just while we're looking at that building, we're thinking of a big rectangular barn or a piece of wood that's obviously rectangular.
Yeah.
But at the end of the day, what's being registered to your eye, what's actually on your retina, are these shapes, not the shapes of the real world. Yeah.
And it's one of these things that people don't. Again, it's the same as what I was just talking about before. People don't realise these things until it's highlighted. It's just, again, things that you're born, you live your life, you take things for granted, and people are not paying attention at the level that we're talking about right now. So
exactly.
Yeah.
Yeah, and I think that's why it's easy for people to tell narratives, because if most of the population or the majority of the population doesn't discern between physical and visual geometry, then there's obviously a lot of scope there to tell a lot of lies of optical phenomena.
Well, every con relies on the participants' ignorance. So, it's just the same here, just as you say. If you don't comprehend it, you're not paying attention to it, it can be used against you.
That's right. And they've certainly done one on us this time. So I'm just going to skip over this one and go straight to what I think is maybe a pivotal piece of knowledge that will help people understand how this trick is being played, if you like. So here's a definition of a nautical mile from a mathematical textbook, yeah? Mm-hmm. And a nautical mile is defined as the length of the arc of a great circle which subtends an angle of 1 minute at the center of the Earth. So you're supposed to believe that the Earth is a big solid ball, yeah, and it has a center. And a nautical mile, as seen here on the right-hand side in an orthographic view, is then the angle, the length of this arc here. So this very small arc, it's the length of that when the angle at the center is exactly 1 minute. And it's seen here, 1 minute, there's 60 minutes in 1 degree. We usually know that a circle has 360 degrees, and each degree has 60 minutes, which basically makes 21,600 minutes in a circle, yeah? And one of these minutes is then the arc length from the center of the Earth is what they define to be a nautical mile. So that's one definition of a nautical mile. I'm going to produce another one here, which is different. This is a practical definition of a nautical mile, and also the way people navigate on water. So the way it's defined is that a nautical mile is the length or the distance that you need to travel to see a change in altitude of 1 minute of something. Yeah. So altitude is basically the visible position of, let's say, a lighthouse. So here's a lighthouse on the left-hand side. There's me at this position, and you, Dale, slightly closer to the lighthouse. Now we are going to see that light in a different visible position from each other. Yeah. And if we wanted to calculate the distance between us, if you see that light 1 minute dropped in your visible vision than me, then we know that we're 1 nautical mile apart.
Yeah.
And that's the way people navigate. Normally they don't use lighthouses, they'll use the sun or the moon. They'll take a sighting, and that way they can to travel. So that's the whole concept of the celestial sphere, which I'm not going to get into in too much detail. But the important thing is here, if you distance yourself from an object, in this case a light tower, and the thing drops 1 minute in your visible place, or its visible position in your field of view, then you've traveled 1 nautical mile. And that's the way people navigate all around the world, Dale.
Yeah.
Today.
Yeah.
And you'll see that these two different definitions are completely different, right? So this one is relying on a mathematical model telling us that we're on a ball and defining what a nautical mile is based on the idea that, the Earth is a radius and there's a ball. In fact, they say that a nautical mile, the radius of the Earth is 3438 nautical miles. So that's a mathematical concept. And this one is a practical concept. You're on water, we know water's level, and if you move backwards from a luminary or from a light in 1 nautical mile, then it will change its visible position. It will basically drop in your visual field 1 minute, 1 arc minute. So given those two different definitions, the question that really comes up is, which one's real? This is the one they all want us to believe, right? And this is the reality of the situation. Yeah. And here's a little bit of text, just for people who want to follow along. And a nautical mile is the length of the arc of a great circle, which subtends an angle of 1 minute. And it also introduces the concept of a radian, which I think I'd like to leave to another day. So I'm just going to use this concept of a radian without completely defining it, and we'll come back to that. Yep. But what happens here is that the number of minutes in a radian is equal to the number of nautical miles in the radius of the Earth. And what pops out basically is this number 3438. Yeah. So that's what they actually tell us the radius of our space ball is in nautical miles. You'll hear different numbers depending on whether they use statute miles or kilometers or whatever. But as far as nautical miles are going, that is apparently the radius of the Earth, 3438. And as I say, there's two different, if you like, definitions. There's the mathematical model, and then there's the practical model. So bearing that in mind, and this number 3438, I'm going to jump differently to a different subject, and then we'll come back to it. The different subject I'm going to talk about is visual acuity and the visual angle. So this diagram is taken from a book about 2020 vision. In fact, it's a book, Dale, that in fact, I think I've got it here. Just let me bring it up. Yeah, I have. This is a book written by an American physics department, and it's to do with what size of letters do you need on an eye chart, right? Yeah. So that they are visible. So when you're doing, your eye test, you usually got one of these eye charts with numbers on it, and you stand 15 feet away from it, and you're supposed to, see if you can read all the letters, and they'll tell you how good or how bad your vision is, right? And this document is talking about the size of the letters that you need to draw and the gaps in between them, so that you can draw signs that are clearly visible, and it depends on the distance and the observer's visual acuity. So it's trying to basically measure visual acuity. Yeah. And if I go back to the PowerPoint, then one of the important topics in here is the fact that your retina is a curved surface. Yeah. And if I'm an eye looking at a chart on the wall, then the question that is asked is, or the definition of a visual angle is this angle here that basically encompasses the whole object. So the object starts at A, it finishes at B. You can think of it as one of these eye charts hanging on the wall. you're at a distance d from it, which might be 15 feet, let's just say, to take an example. And then the question is, what is the angle subtended at the eye from that object, AB? Yeah. And you can work out that angle. On the next slide, I'll just show how it's done. The visual angle is basically the height of the object, or the width of the object if you were looking at something horizontally, but let's assume it's still an eye chart. It's the height of the object divided by the distance from it. Gives you the visual angle in radians. Yeah? And again, I'm using this concept of radians without specifically defining it, but the radians is a way of intrinsically measuring based on the radius of a circle. So instead of using degrees and minutes, you basically use the radius of the circle to measure how far you are around it. So if you like, it's something different to degrees and minutes, and it's called radians. Yeah. So this is clear. The visual angle subtended at your eye depends on the size of the object and the distance you are from it. Yeah. And if you want to convert from radians to degrees, there's a way to do that, which I'll just follow the bouncing ball for those who want to follow along. It basically turns out to be the visual angle in minutes is 3438 times the size of the object divided by the viewing distance. Yeah? So this magic number 3438 pops up again in visual acuity. Visual acuity being how far can I actually see before things are no longer discernible to me. So what's the limits of my vision, basically? And this formula, just to give you everybody an example, would mean that if you had a coin of 1 inch of diameter and you put it at 3,438 inches from you, which is 286 feet or 95 yards or 87 meters, right? Then the visual angle of that coin will be 1 minute. And basically at 1 minute, Dale, that's where your visual discernment stops. So some people can go a bit lower, right? Depends on age and lighting and, various conditions. So this isn't exact, but basically if something is less than 1 arc minute, then you can't see it anymore. And anybody can try this, Take a coin, put it at 87 meters and see if you can see it still. Or take a dartboard, it could be 1 meter. You would then have to go back 3,438 meters and you wouldn't see it. So it doesn't really, it doesn't depend on the size of the object. The formula is there all the time. And this magic number 3438 is there in the whole topic around visual acuity. And it just happens to be the number of nautical miles in the so-called radius of the space ball. So people could think this could be a coincidence. I don't think so, right? That basically this ratio of 3438 is where, if you like, the imaginary curve is supposed to happen. Do you know what I mean? Just beyond our limit of vision, is where the curve starts.
Well, you see this in horizon images of ships apparently disappearing. And it's always the same when you ask the question, well, why does it appear to be a ramping up and then at the point of the horizon it dips away? So as you say, this is the point at where they're saying that the curve is, that's when you're witnessing the curve of the Earth.
Exactly. Yep. So I'm basically showing now that the Nautical Mile has the number 3438 involved, and visual acuity also has 3438 involved. And there's this concept of radians, which seems to be common to both of them. And radians is, as I say, it's a mathematical definition. If you like, it's a generic way of measuring something around a circle or around an arc that is dependent on the radius of the circle to begin with, and not on an arbitrary number like 360, and then dividing it into 60 minutes. I think the reason they chose 360 might have something to do with the the duration of a year if you leave 5 days out for when the sun doesn't change its position, like at Christmas and at summer. And 360 is one of these numbers that's easily, divided and multiplied by a whole number of factors. So it was very, how should I say, it's a good thing to do if you're doing calculations.
It's convenient.
But radians is a different way of doing it, And radians basically takes away any concrete measurement and leaves it solely dependent on the radius of the circle that you're playing with, right? So it's a kind of generic way. It's a kind of abstraction, Dale. So you're not actually getting out anything and measuring a centimeter or an inch, because it's dependent on the radius of the circle that you're drawing. So we've shown that there's a connection between these two things, right? That might or might not be obvious to people. It's certainly nothing that I ever got taught, Dale, when I was studying this stuff. So again, it seems to be tying two different fields, i.e. you going to an optician and getting your eyes measured, right? With the stuff they're telling us about an earth ball, and space balls. So one of the things so I'm just going to leave that as a kind of background to the next topic. And the next topic is actually to go into more detail about the geometry of vision and look at some of the, let's just say, the basic things that people should know. And that might actually, after we go through this part, might be a good place to stop, Dale. And I was thinking we should do a follow-up on this, right? Where we go into more detail. So this is the slides I'm going to show now are taken from a book, my favorite philosopher, Thomas Reid, who has a chapter in his book, Inquiry into the Human Mind on the Principles of Common Sense, and that chapter is called the Visible Geometry, or the Geometry of Vision. And what this chapter talks about is basically a proof that your vision is spherical. It's got nothing to do, it's not Euclidean, but the fact that your eyes are globe. I mean, it's kind of obvious when you think about it, right? The fact that your eyeball is spherical, but the geometry of vision is also spherical. So let's just go through it. There's a couple of things that people just need to remember when they're thinking about this topic. So the first thing is always to imagine that your eye is at the center of a sphere. And a great circle of a sphere is basically, if you cut a plane through a sphere or a ball, then where the plane meets the surface, you're going to have a circumference, a circle made. And that circle is called a great circle. And if you were at the center of a sphere and you looked at that great circle, you would not see it curved. Because you're looking straight at it, you wouldn't see its outward turning or its outward curviness. You'd see a straight line.
So what I was trying to make, just to add in here, just to inject this in, if people had a nice shaped hula hoop, so made of metal, nice and flush, and you turn the hula hoop up on its end and place it in front of your eyes, you're just going to see a straight line. You're not going to see the outward curve at the other end. Or even if you were in the centre of a hula hoop and you lined it up to your nose, you're just looking at a straight line. You're not seeing the outward curve that goes around the outside of it.
Exactly, and it's the same for your horizon, basically. If you look around you, all you need to do is turn on the spot and let your eyes travel round with your head, and you will also have the impression that everything is a straight line. And what you've done is turned a circle. So again, that's a great circle as well, the horizon around your eyes, and for us it's a straight line. And the second paragraph that says here, and it's important to note too, that if you put a plane through a sphere, and on that plane you draw a squiggly line, then again you won't be able to see that squiggly line, because again, it's like side on to you, right? You're looking at it, even if it was whatever kind of curves, all you'll see is the points as if they were organized in a straight line again.
Yeah.
So it doesn't matter whether they're straight or curved, they'll always look straight to you. Yeah?
Yeah.
And it's basically because you're at the center of a sphere, and these things, you cannot see the curvature because you're looking directly at them. So that's, one of the main propositions, let's say, of the geometry of vision, that you, how should I say, understand or comprehend this part, right?
Yeah.
And I think it's similar to also if you take a pencil, Del, and you put it out in front of you, then all you see is a point, right?
Yeah.
You see the end of the pencil, you don't see the line, right?
Yeah.
So similar stuff.
Yeah. I was just going to jump to the whiteboard here just to show what Gav's mentioned. So, we got a circle, you got a squiggly line like this, right? Obviously for the orthographic view, but if we were to be looking at it from this point of view, looking at it here, it's going to appear like that. I know that's not a perfect straight line, but that's what you're going to see. You're not going to see these peaks and troughs. Same for the circle, you're just going to see a straight line looking at it from that point of view. It doesn't matter if you do it vertically or horizontally, it's the same principle.
Yep.
That's you back on, mate. Sorry, I was just showing it on the whiteboard there.
No bother. We got whiteboards now.
Digital
whiteboards.
We've got an online digital whiteboard with squiggly lines.
So I'll just go on to the next thing. So when we talk about, I hope the PowerPoints or the slides visible. Yeah.
Yeah.
So when we talk about a visible right line, then we're talking about always when the word visible is in there, then it's what we're seeing, right? So I'm looking at a visible straight line, and it's always going to coincide with some circle of the sphere. Because if you have a line, Dale, and you're looking at it, then the outside arc of that line. Sorry, I know we don't have a picture to show here, so I hope the words themselves will get it, or we'll say an example in a minute. But they'll always coincide with a great circle of the sphere. And when you produce those lines, so like what I said about the horizon, it will appear to be a continuation of itself, and it will return on itself. Yeah. So the example I gave of me just standing there and turning on the spot and looking at the horizon, it's a straight line. It joins up in itself, right? And it's a continuation basically of one line all the time. Yeah. And the eye doesn't see those objects, or it's only the position that it sees with respect to itself, and never sees the outward distance.
Yeah.
So the points on a great circle will have the same visible place as the points on the line will have. So maybe it'd be better to have a diagram for this, but I hope everybody can maybe just come back and read this themselves until they've understood it, or they can ask questions or whatever. But these 2 points are important.
I think we do need to keep coming back and visiting this and continue it on as a series, Gav, to be honest with you.
Yep. The main thing is that both, because the points in great circles have the same visible place as the points on the line that you're seeing, then basically everything can be represented by the great circles of a sphere. So here is a diagram which I hope kind of makes it a little bit more obvious.
Yeah.
Here's a great circle around the sphere. You can see that the points on that sphere are basically the representation of that line, which is drawn in a plane, in this case, below your feet or below your eyes. Yeah. But you can see that line is perfectly represented by the points on the great circle. So every line has its own representation as part of a great circle.
Yeah.
Yeah. It doesn't have to be a full great circle. It can be an arc segment of a great circle, but basically every line will have that. Yeah. Now, if you have two lines, like let's say there's another line there, then it will also have its own great circle. Yeah, so you could imagine this diagram having two great circles, not just one, and you're maybe looking at two lines. Then there will be two great circles, basically, on this sphere. And basically what we're saying is, if you see the angle of these two lines that are drawn on the ground, it's the same angle as the spherical angle that the two great circles make where they intersect. Yeah. And this is a well-known fact. This is a very important slide, this one, and the text that's on it, which basically summarizes what we've said. And this is something that mathematicians know, that the visible angle that comprehended under two great circles when seen from the center is the same magnitude as the spherical angle which they really comprehend. So on a ball, yeah? So if you're looking at something from the center of a sphere, then the visible angle made by two great circles is going to be the same as if you measured the spherical angle on a real solid ball. Yeah? And that might sound trivial, what I'm saying, but it's a really, really important point to understand how the trick works, yeah? Because if you think back to this definition of a nautical mile, i.e., we're supposed to believe that we're on a space ball which has a center, yeah? But what they're really selling us, yeah, is the geometry of vision. They've just packaged it differently, Dale, yeah? Using that this slide here basically gives most of the game away. Yeah. If you understand this part as mathematicians do, then you also realize how they can quite easily swap out the one for the other. Yeah. Because the angles they're measuring, the visible angles, think back to, I'm on the water and a lighthouse is dropping its visible position. Yeah. And if there was two lighthouses, then I could draw a line and I can measure angles, right? Yeah. Or with a sextant. They're basically saying that on a ball, the spherical angle will be the same as that visible angle that you've done. Yeah. So that's how they can get away with putting you or saying that it's the same as a ball. Yeah. And they've even made the definition of the nautical mile such that it works. Yeah. So I hope that makes sense. Well, it's a complicated subject.
So get back to the whiteboard again. Where's my rubber? Wait a minute. Just quick, just so I can. Wait a minute here. What is going on? Let me put this away up here so I can rub this out quicker. 2 seconds. So for me, what Gav's saying here is, and just stop me, Gav. I don't know if you can see me on the whiteboard here.
I can.
Right, okay, right. So, what Gav's saying, we've got the lighthouse here, we've got the observer here, and there's an angle, right, that you're looking at it. Right. Now, as you move back to here, obviously the angle's decreasing. So what's being done is that this is just based on the arc of your vision, that this is happening, so you can see that there's an arc here of the outer portion of your vision. But as you walk back, what they've done is they've made you think that you're walking backwards over a curve. And is that right, Gav? Am I right, correct here?
Aye.
So it's just a switch of the two geometries again, and superimposing that it's a physicality of you moving around a spherical object. Am I right?
Yep.
Right.
Absolutely.
I'm just trying to do it quick here, with this squiggle, but
your artistic abilities are pish.
You do it with a mouse.
You really need one of these tablets and pens.
So I mean, as you walk back on a level surface, the top of this is appearing to you to drop. So now that you're back here, the top for say would be appearing here, right? And what we're talking about is vision and the angle of vision with the outward arc of your vision, right? Because you're not seeing this curve point, right? You're just seeing the inside of it, if you like. But as you walk back, rather than this dropping in the visible field, they're trying to make you believe that it's staying still, but what's happening is you're going backwards over a curve, so this appears to drop due to you walking back over the curve of the earth. Correct?
Yep, and it's got nothing to do with curvy spaceballs and everything to do with how your vision works, because the spherical geometry is the same in both, and it's just a matter of making definitions and using the language Dale to tell the story. So if I was to go back to the one about the visual acuity, where was that slide? Yeah, so this visual angle, the size of the object and the viewing distance. You've heard the old story about the moon is apparently, a lot smaller than the sun. They just look the same size because one's so far away.
Yeah.
So if you're obfuscating angles, or you're using angles in this concept of radians to measure things in astronomy and celestial sphere, then you can tell lots of stories about the size of the object and the viewing distance to make it fit, Dale. Whereas if you're standing in front of an eye chart, it's 15 feet, and you know that it's 5 foot tall, or whatever how tall they are, I don't know, right? So, getting back to the fact that we can walk to the chart, right? We can measure its dimensions using a ruler. We can pace the distance, So it's all right to use it in that respect and to talk about visual acuity, but it's very easy for them to use the concept of radians and talk a lot of shite about the size of objects and the viewing distance, Dale. And again, that for me, that's where the trickery comes into play. I think the next thing I'd like to do is dive into this concept of radians, and unfortunately, it just gets a bit mathematical. And I'm assuming that there needs to be a certain amount of knowledge right around mathematics, which makes it kind of difficult to convey to everybody. But I'd like to try my best the next time to go through this concept of radians so that it becomes clearer how they're making this trick. So if I go back to the geometry of visible space and the geometry of physical space, making sure that you understand that difference is absolutely imperative, right? And that they can get away with using it in astronomy and navigation only because they're actually using visible space to do their calculations, the geometry of vision, rather than the geometry of any real spaceball, Dale. And the concept of radians plays a big part in that.
Which again it's backed up by the very fact that they don't have a direct measure, as we were saying at the very beginning of this. There is no direct, tangible measure of the curve of the Earth.
No, absolutely none. So that's all I've kind of got as a kind of way to get myself back into the swing of things, Dale.
Nice one.
To say it's been a while, and I just thought it makes sense to revisit this topic, and I'd like to dive in a little bit more into some of these mathematical concepts and hope that I don't lose people along the way, because I know it is not a simple thing.
To be honest with you, if people are really curious and interested about the nuts and the base of this is where you have to go. So there's too many people out there that are just interested in entertainment and pacifying themselves for selfish reasons, but if we want to get at the root of this whole thing, then this is where we need to really go.
Well, I think it's imperative that we wake up the people that are in the science field, because again, even though I know that there's a lot of corruption and nonsense done there as well, Dale, I still do feel that people with integrity inquiring about the nature of the world, they don't know this stuff, and they don't make the discernment between visible space and physical space. And if they did, then we might have more people in the science world coming out and understanding and realizing this whole con.
It's no part of the curriculum, and getting back to what that person was talking about earlier, and people telling lies and blah blah. They just don't comprehend this stuff, and just because they're in academia or they've got PH, whatever after their name and letters, it doesn't mean to say that they've contemplated or even reasoned with this stuff. because it's not been made relevant to them, because obviously they're born into the same situation that we are, and they're just operating from the assumption and the ignorance of that assumption, and they just continue on their path, rabbiting and repeating from that perspective. But this stuff that we're talking about now is demonstrable. It's a fact, that we're talking about two different geometries. There is a definite geometry to vision, and how anybody can possibly try and deny that is mind-boggling. And then it just becomes a comprehension of how do we separate the visible space for the physical space.
And I'll reiterate what you said many a time. Anybody who is not taking visual perception or the geometry of vision into account in the explanation of any of their optical phenomena for their proofsies it's just ignorant, or not being honest. One of the two.
This is why the globe proponents are continually showing people orthographic projections of, like, we'll say fence posts, and asking questions of perspective views of how something taller than this one can appear below this one, and because they're flipping between the geometry of physical space and how objects actually are in the visible space, then omitting that there's a geometry to vision, and then making assertions and statements about what we should and shouldn't see, in the visible field, without accounting for the visible field and how it's actually functioning.
Absolutely, and this jump to an orthographic view denies how we actually look at things. We look at things directly, Dale, in a globe, like at the center of a sphere. So jumping to an orthographic view it implies that you've got some kind of godlike powers to be able to, extract yourself from whatever it is you're viewing, all the way out into outer space to be able to look down at that, which you can't, I mean, one, because it's not real what they're telling us, and they tried to give us these kind of godlike abilities, if you like, to sell us then the stories.
Exactly, and the orthographic view is perfect for us in regards to construction and these types of things, because it works for us. That's how the world functions. But that's to do with tangible objects that that have a direct measure. Totally different from how it appears to us visibly.
Good. I hope that kind of made sense to folks who may be hearing it for the first time, and for anybody who's already heard it. Repetition goes a long way sometimes to helping understanding or just talking about it. So,
well, I often wonder about new people. I keep seeing a lot of social media, TikToks and whatever else, and there appears to be a new wave, if you like, of people coming into this topic. So again, none of us have all the answers, and it's good for me, it's good for you, Gav, to go over this stuff and continually push to see where it takes us, because for me it's pointless arguing and debating about flat earth, globe earth and all this other stuff. If we're going to use visible phenomena, or ships go over the curve, ships don't go over the curve, we see too far, on both sides of the dichotomy, that people are still omitting that there's something that has to be looked at here in regards to the geometry of optics. So
exactly, I think it applies, as you say, to both globe believers and if you want to call them flat earthers or people who don't believe the globe, this part is, if you like, for most people, it will be the missing link. Again, it's not a proof of anything. Water already proves, that they're telling us lies. But the how, how they've done it and how they're deceiving us, this has a huge role to play, Dale.
Well, that's the power. That for me is the useful aspect, because